Good morning, sir. Today we're going to talk about our story about this paper on approaching, integrating, simulating, and annealing and variable neighborhood search for the bidirectional loop layout problem. Now, next slide, please. Now let's get into the introduction. This paper is about the study of machine layout problem that can be modeled by presenting a solution as permutation of machine to be assigned to a given set of locations. Low or unlow may be considered a starting point of the loop. In the remainder of this paper, we refer to describe problem as bidirectional loop layout problem, or BLP. The objectives of the problem is to determine the assignment of machine to location which minimize the sum of the products and the material flow cost and distance between the machines. Next slide. As you can see, the example of the loop layout machine M3, M1, M6, M4, M7, M2, M5 are assigned to location 1, 2, 3, 4, 5, 6, and 7. The numbers on the edge indicates the distance between locations. Next slide. The bidirectional loop layout problem is applied to in the design of flexible manufacturing system (FMS). The loop layout is one of the most preferred configuration. In FMS, the BLP can be expressed as the following formula. Next slide. In summary, our motivation is to investigate and implement new strategies to create meta-heuristic-based algorithm. For the BLP, our specific goals is to improve the result obtained by the HS algorithm. Overall, the focus of this paper is on the variation of the loop layout problem, where the AVG is allowed to transport the material bidirectionally along the loop. Next slide. Okay, let's move to the second section, integrating SA and VNS. Next slide. The basic idea of the VNS method is to explore the neighborhood of the currently best file solution. We implement this strategy by combining VNS with the SA algorithm. Therefore, our idea is to speed up this process by starting VNS with a solution generated by another heuristic. Next slide. This is the flowchart of the SA and VNS hybrid and the algorithm of integrating SA and VNS, which we will talk more in the next part.
So in the third part, we will talk about simulated annealing. Next slide, please. First of all, we're going to talk about what are the basic concepts of simulated annealing. So simulated annealing is a mathematical and modeling method that is often used to help find a global optimization in a particular function or problem. Simulated annealing gets its name from the process of slowly cooling metal, applying this idea to a data domain. Processes like simulated annealing are used to build more sophisticated operations that, while working on more complicated set of rules, developers create efficiency related to their goals. Next slide, please. So, particularly in the paper, we have the suggest that suppose L belong to K. In this part, K7 equals to 8, 9, 1, 0, and 1, 2. K8 plus equal to 9, 0, 1, 2, 3, and K8 minus equal to 4, 5, 6, 7. Let's donate the set of domains assigned to location K plus by MK and those assigned to location K plus by MK minus. So we noticed that since the machine R is being relocated, MK plus is not necessarily really equal to L belong to K plus, where P is permutation. So guess which 10 procedure is applied to which remains untouched during an execution. Next slide, please. So the next part is to suppose LK else is smaller than K. If L is smaller than K, we evaluate the impact of machine in location J equal to K plus Q1 and move again. For such J, we know that dq plus 1J smaller or equal to d minus q plus 1j. This implies that the change in the distance between R and machine in the location j are the same, and the distance change for the machine p, q, and s is exactly the same with the opposite sign. So we get the expression as follows. Next slide, please. And the last part of the simulated annealing program is the computational complexity of the procedure to get gain on ON. In this part, we don't use the first method. We use the procedural code of a VNS method and apply it to the simulated annealing. We insert arterials through machine U belong to MQ plus divided MQ plus Q minus 1. And for such U, the entropys and in most cases are updated beside the case where U represents and ULU station, the entry BU remains unchanged. When U equal BAQ and NQ equal to 1 and illustrate this part of the process. And by checking the examining permutation, so in the two figure in the picture, we pass through the first domain root and up insert ends by adding CSR and BS and swapping position of machine R and S equal P, Q in P. Illustration of the insert procedure where Q equals to 4 and S equal to P, Q equal to 5 if R equal to 9 and Q equal to 3. Initial solution and solution obtained by the interchange machine R and S are shown as the two figures in the slide. So the next part is the fourth part. My friend will present it.
So in this part, I will talk about variable neighborhood search. Firstly, they assume that if the pre-specified single time limit for the running SAVNS has not been reached, so the best solution to found is that pass to the VNS component, which is exploit a combining of neighborhood change mechanism with a local search technique. To implement this problem, they define the neighborhood structures used in the shaking phase of the method and choosing a finite set of neighborhood structures, which consists of all permutations that are obtained from P. Next, please. Here is the sort of course of the VNS method. Next. The method can be configured to use two different local search. This is done by setting an appropriate value of the flag parameter. There is two conditions. If the VNS is equal to 0, then we apply the pairwise interchange. Else, if the VNS is equal to 1, they will apply the use of machine insertion moves. Next. The parameter that apply to control the search process is K-min is the size of the search that is started from. K-max is the largest possible size which computed and kept unchanged during the execution of the inner prior loop spanning. The case step is moved from the current neighborhood to the next one, which should set to max when the K-max has been computed. Then they note that K-max and K-step vary as the algorithm progresses. Next. The inner loop of VNS repeatedly applies a series of procedures, including check, which generates a solution P by performing a sequence of random swap moves. The neighborhood change is responsible for updating the best solution found. The local search interchange and the local search insertion. The local search interchange, which applied in this paper, used to search for a locally optimal solution. Next. Here is the algorithm for search function and neighborhood change functions. For local search insertions, firstly they initialize the array P. The variable Triangle star is the best move found, which is returned by explore neighborhood procedure until there is no improving move is possible. The main part of this procedure is the same pattern as get gain in algorithm tree. The best insertion move found is represented by four tuples. Triangle star is the gain, R star is the new machine, L is the new locations, and beta star is the value of the move star. If the triangle star is less than 0, it proves that an improving insertion move was found. Next, please. Here is an algorithm of insertion-based local search. Next. The same complexity can be achieved in the case of the insertion neighborhoods. They substitute line 6 of the explore neighborhood with lines 6 to 12 of get gain. This will create the form has triple nested loops. Nevertheless, the insertion neighborhood and the interchange neighborhood have the same worst case time. Next. The proposition 3, the computational complexity of the procedure explore neighborhood is O with the n power to 2. The proof that from the proof of proposition 1, each iteration of the outer for loop of algorithm 9 takes O operations. This will executed for each machine. According to proposition 2, insert runs in linear time. Collectively, these facts imply the claim. Next, please. In part 5, my partner will talk about computational experiments.
Okay, I will cover some key points about the section 5 computational experiments. So the purpose of this session is to examine the computational performance of the described simulate annealing and variable neighborhood search hybrid. So we have the following for that data set and measurements, which is shown on the screen. And also on the setting parameter, we have demonstrate the appropriate one to their algorithm, which is shown on the screen. And this parameter has been tested and evaluate carefully in order to choose the best one. Okay, this is the comparing of the SA and VNS versus its component. As the result we achieve is suggest that SA1 is the best performing algorithms among the test versions of SA and VNS. In the main experiment, we therefore select SA1 as the representation of the set of non-hybrid algorithms. We will continue to evaluate the performance of SA VNS. So in table 2, the result is showing BLLB instant in the SKO dataset. And in table 3, we report the average running time to the best solution in the run of each algorithm. Overall, we can conclude from table 2 and table 3 that SKO instant are not challenging enough to our hybrid SA VNS hybrid. In table 4, we saw the results obtained by SA VNS and SA1 algorithm for larger scale BLLB instant. For table 4, it can be seen that SA VNS one outperform the other ones, and as well as SA1. Next, we can see the gap for calculate the result of benchmark instant for the tools index problem is shown on the screen. So in table 6, we can compare the values of F average, and we can also see SA VNS 11 consistently outperforms SS for all 24 instance. So for table 6 and 7, one can see that SAVNS11 did not success for all run in 15 problem instance. So to answer this, we given the table A, where is the second column stand for the average time take per run, and the third column report for the CPU times for the longest run. As we observe, for example, the SAVNS11 can find the best solution in 70 seconds with the probabilities of 50%. And that concludes my section. We will jump to the next one, which is presented by Doug.
For the next part, we will discuss about, next slide, please. For two databases as equidistant and their own dataset, which are publicly available and could be used as benchmark to design and solve the BLLB with a new methodological algorithm, which consists of large-scale BLLB instances for 150 more machines. Various configurations of SAVNS were able to find the best solution in multiple time, which showed the robustness and effectiveness of the method and excellent performance in solving the TIB. From the table 6 and 7 above, SAVNS is superior to the SS heuristic. Together with table 4 to 5, SAVNS also perform better than earlier algorithm for this problem, which result in this paper. SA and VNS are very successful techniques. Next slide, please. As noted, the main goals develop a methodological algorithm and compare the performance. The special case of BLLB. In the past, many technical proposals and direction of layout problem, BLLB is perceived to be more difficult than ULLP, and one of the reasons BLLB received less attention in the literature as outlined the existing algorithm for the BLLB are exact or approximate methods. According to the researcher's knowledge, methodology-based algorithm is not presented to solve this problem. They are proposed an algorithm combining SA with AVNS methods. In the absence of other methodological algorithm restricted to test the configuration of SAVNS. Next slide, please. The effect of using the procedure get under dash gain and explore under dash neighborhood is described accompanied by proportion 1 and 3. First, elementary get under dash gain from SA replaces statement in line 14 in algorithm 2 by a statement limited to the one in line 11. Compute delta bằng FB dot minus FB, where B dot formulation obtained by B by removing machine R from its current position in P insertion at position 1 F B dot taking ON time to time as opposed to ON time stay in proportion 1. The method modification of SAVNS 1-1 denoted by SA dot VNS dot -1-1. They perform computational experiment at the same time the TIB instances. The results are detailed in table 9 and 10. The percentage gaps GAV calculate for FAB in column 3 and 5. For the second comparison, SAVNS 1-1 is in table 6 and 7. Next slide, please. After eliminating get dash gain replacing explore neighborhood, which is calculated by the gain delta value of a function f and each permutation in the n1, which is larger than complexity explore neighborhood in proportion 3, denoted by SA dot VNS dot 1-1, shown in table 9 and 10. Modification of SAVNS 1-1 produce inferior solution, which the reason is run slower compared to SAVNS 1-1 and often fail to come up with a solution of highest quality, especially in all 30 runs. Both modifications fail to find the best solution. So get gain and explore neighborhood are both important ingredients. Next slide, please. The heuristic employed in the research study advantage and disadvantage compared to optimization techniques. A well-known drawback of SA is slow execution of this algorithm takes large amount of computer time. So for that, using a 5 procedure compute gain. Another weakness is trapped in a local minimum. Solution is submitted to the VNS algorithm, which partly compensate the mentioned weakness. However, VNS methodologies had disadvantage. It is difficult to determine appropriate neighborhood structure in the researcher's implementation. It is defined as the settable permutation, a possible direction. Try different neighborhood structure for VNS in the BOLP. Next slide, please. So in conclusion, the important result of this paper is local research technique that based on a certain neighborhood exploration procedure, the computational complexity of this procedure is commensurate with the size of neighborhood. That is, it is performed operation per move. This LS algorithm stands as the heart of our VNS implementation. We have shown empirically that the variation of the instruction move in neighborhood definitely gives better result than a variation of the algorithm SA or VNS. Compared to perform pairwise intelligence of machines, computational experiments will carry out on a large scale instance of the BLF. SA and VNS hybrid algorithm is superior to both SA and VNS used standalone. Next slide, please. There are several issues where further research is considered to be valued. Effort can be oriented towards improving the speed of precision outcome for the BLB and TAB. Population-based evolutionary algorithm may provide an advantage over local research-based techniques like SA and VNS. Another way to use the SA and VNS hybrid method is a basis for developing suitable algorithm for solving layout problems that are generalization of vibration for the BLB. It would be intriguing to investigate the performance of the process algorithm on a very large scale of BLB and TIB instances and find a good balance between the quality solution and the computation time. That is the end of our presentation.